Howdy, this video is on complex equilibria. Most chemical systems are more complex than the examples that we often use. Most systems actually contain multiple equilibria. Now when you have multiple equilibria, all the equilibria have to be satisfied. Biological systems are very complex and often have multiple equilibria. After watching this video, you should be able to determine the concentration in the solution where there are multiple equilibria present. You should be able to determine solubility of a solid when there's a common ion already in solution. You should be able to determine the effect that pH has on the solubility of different compounds. And so if we add silver iodide to water, enough silver iodide will dissolve until we get to that minimum. Remember, systems want to get to the lowest the minimum energy, the minimum in free energy. And so you add silver iodide to water, it will dissolve until you get to that minimum. If you keep on adding more silver iodide to the water, no more will dissolve. The most simple configuration for a solution is when the silver ion concentration times the iodine concentration equals the KSP, which in this case is 8.3 times 10 to the minus 17th. Now a question we could ask ourselves is, what happens if a saturated solution of silver iodide, now again, saturated solution means that you're at that minimum. And so if a saturated solution of silver iodide is at equilibrium and then some sodium iodide is added. Now sodium iodide is a strong electrolyte. Now being a strong electrolyte means that the sodium iodide will dissolve into ions, because it's the definition for a strong electrolyte. And so if you add sodium iodide, you're going to add sodium ions and iodide ions. And so what's going to happen is the iodide ions concentration will increase, and so that will increase your Q. Remember, for the silver iodide reaction, the Q is equal to silver ion concentration times the iodide concentration. And so if you add the sodium iodide, iodide ions will increase. Now what will happen is the system wants to get back to equilibrium, and so some more silver iodide will actually form to get you back to equilibrium. Remember, the minimum is the most stable. System wants to be at a minimum. You can kind of think about it as a boulder in a valley. If you push the boulder up to the right, the darn thing just rolls back down. And this is actually the basis of Le Chatelier's principle. Le Chatelier's principle says that if a system's at equilibrium and then it's disturbed from equilibrium, it will try to reestablish equilibrium by countering that effect. And so that's what we saw here. We were at equilibrium, we added some iodide ions, so that disturbed it from equilibrium, that pushed the boulder to the right. The system then consumed some of those iodide ions, getting back to equilibrium. We had pushed the boulder to the right, the dang boulder just rolled back down. And in this case, we didn't have to worry about the equilibrium for the sodium iodide because it is so large, so we just consider it as if it went to completion. And so we could ask another question: what happens if a saturated solution of silver iodide, again, saturated means that we're at that minimum, is at equilibrium, and then some more silver iodide solid is added? Well, remember, the system will only respond if Q no longer equals K. And so if we're at equilibrium and then we add some more silver iodide solid is not in our Q expression. Q is equal to silver iodide times concentration times iodine concentrations. And so adding more silver iodide solid does not change anything. But we could also ask another interesting question: would silver iodide be more soluble in pure water or in a solution of sodium iodide? Now what we'll see is that because of the common ion, iodide minus, the silver iodide should be more soluble in pure water. But we can actually calculate this out. So we can calculate the solubility of silver iodide in pure water and then calculate the solubility of silver iodide in a 0.1 molar solution of sodium iodide. And so this is just a solubility problem. And so we can make our ice table initial change equilibrium. I'm just have the equilibrium here, and so if X of silver iodide solid dissolves, we'll get X of silver ions and X of the iodide ions. Now the KSP is equal to products over reactants, coefficients become exponents, pure solids, pure liquids do not appear, and so our K is just equal to silver ions concentration times iodine concentration. Remember, solids do not appear in properly written equilibrium expressions. And so we're saying that at equilibrium, silver concentration should be X, iodine concentration should be X, and so X times X gives us X squared. So KSP for this reaction is equal to X squared, where X is the concentrations at equilibrium. Now if we take the square root of both sides, we get X, which is our solubility, is equal to the square root of the KSP. Our KSP is equal to 8.452 times 10 to the minus 17th, and so that gives us a solubility of 9.23 times 10 to the minus 9th. capital M is molarity, which is moles per liter. And so the solubility of silver iodide in pure water is 9.23 times 10 to the minus ninth. Now we can actually calculate the solubility in 0.1 molar sodium iodide. Now we do it the same way. Initially we had 0 of the silver ions on the previous problem, but here we're saying that we're starting with a 0.1 molar solution of the iodide ions. Now I'm going to use Y for solubility because we have a common ion. And so when Y of silver iodide dissolves, you'll get plus Y of silver ions and plus Y of iodide ions. At equilibrium, we have initial plus the change. And so that gives us Y and 0.1 plus Y. Now, notice our KSP is really, really small, 8.52 times 10 to the minus 17th. K is products over reactants, and so if your K is really small, it means you're going to have mostly reactants at equilibrium. And so most likely the Y is going to be negligible compared to the 0.1. And so we'll use the approximation of that we can neglect Y. And so that gives us the silver ion concentration as Y and the iodine concentration as 0.1. And so KSP is equal to silver ion concentration times iodine concentration, which is equal to Y times 0.1. Now if we divide both sides by 0.1, we get Y is equal to KSP over 0.1. And again, Y in this case is the solubility in this solution of 0.1 molar sodium iodide. And if we do the math, we get 8.52 times 10 to the minus 16th. And so notice that in pure water, it is 7 orders of magnitude, 1,000,000 times more soluble in pure water than it is in solution of sodium iodide. Now this is referred to as the common ion effect. And so weak electrolytes are going to be more soluble when there is not a common ion. When there is a common ion, then a weak electrolytes are less soluble. And so the dissolution of a weak electrolyte is decreased by adding a strong electrolyte that has an ion common to both. And so again, the solubility of the silver iodide decreased when we added the sodium iodide, which is a strong electrolyte, because it had a common ion, the iodide minus ion, to both. And again, we can understand this based on Le Chatelet's principle. Now we can look at something slightly different. And so if we add a saturated solution of calcium fluoride at equilibrium and then some hydrogen ion is added, will Q change? Now calcium fluoride dissolves in the calcium ions and fluoride ions. And so the question we should ask ourselves is, will the hydrogen ion react with either the calcium ion or the fluoride ion? Now we should recognize, or remember from that table where we had acid, base, acidic, basic, and neutral, alkali metal ions are actually neutral, calcium ions are neutral, and you should recognize that the fluoride minus ion is the conjugate base of HF, and so fluoride minus ion is going to be basic, and so hydrogen ions should react with the F minus ion. And so the moment after hydrogen ions react with F minus ions, does that mean Q would be greater than K, less than K, or equal to K? Now if we look at it, and so basically what we're saying is that the fluoride ions are going to react with hydrogen ions. Now Q is equal to calcium ion concentration times fluoride ion concentration squared. And so if we remove the fluoride ion concentration, our Q is going to go down. And so the system's going to go to the left. Now obviously we're no longer at equilibrium, and so what's going to have to happen is more calcium fluoride is going to have to dissolve to get back to equilibrium. And so again, this is an example of Le Chatelet's principle. Our system was at equilibrium. We added some hydrogen ions. It consumed some of the fluoride ions, pushing the boulder to the left. The system then responded by letting the boulder roll down to the right by dissolving more of the calcium fluoride. Again, just an example of Le Chatelet's principle. Now we can ask a related question: should calcium fluoride be more soluble in an acidic solution or a basic solution? Well, we just saw that if you're in an acidic solution, then the hydrogen ions consume the fluoride ions, and so the calcium fluoride should be more soluble in an acidic solution. And it's actually pretty pronounced. We can plot the solubility of the calcium fluoride as a function of pH. And notice that the pH is plotted going from big numbers to small numbers. And so as you go to the right on that graph, you're going to a higher concentration of hydrogen ions. Remember, the lower the pH, the higher the concentration of hydrogen ions. And so the lower the pH, the much higher the solubility of the calcium fluoride. We can ask a related question: will the silver cyanide be more soluble in a solution with high pH or low pH? Again, remember, high pH means that you're going to have very few hydrogen ions. Low pH, you're going to have a lot of hydrogen ions. Well, we have to recognize that silver cyanide is going to dissolve into silver ions and cyanide ions. You should recognize the cyanide ion as the conjugate base of HCN. And so cyanide ions are going to be weakly basic. And so they'll react with hydrogen ions. And so silver cyanide should be more soluble the lower the pH. And so again, as you consume those cyanide ions, the system has to dissolve more of the silver cyanide. And again, this table is really helpful. It talks about acidic, basic, or neutral. And most of this is conjugate relationships. And so you should remember, on the bottom right, conjugate bases of weak acids are basic. Conjugate bases of strong acids are actually neutral. And then on the top left, conjugate acids of weak bases are acidic. And then if you look on the left, on the neutral, group 1 and group 2, that's the alkaline metals and alkaline earth ions are neutral. Small highly charged metal ions are acidic. And then top right, you see the hydrogen sulfate and dihydrogen phosphate are acidic. But this table is very helpful to understanding if a compound or if an ion is going to be acidic, basic, or neutral. And then it's important here because we're asking, will it be more soluble the higher the pH or lower the pH? And so you have to look at the ions that the solid dissolves into to determine if it's acidic, basic, or neutral. From that, you can determine if it will be more soluble in a high pH or a low pH. So will ammonium chloride be more soluble in a solution with a high pH or low pH? And so again, recognize ammonium chloride dissolves into ammonium ions and chloride ions. Remember, the polyatomic ions are important because they stay together as a group. The ammonium ion is a polyatomic ion. Now you should recognize that the ammonium ion is the conjugate acid of a weak base. And so it's going to be acidic, and so it's going to react with hydroxide ions. And the higher the pH, the more hydroxide ions you have. And so ammonium chloride should be more soluble the higher the pH. And again, you can think about this in terms of the Chatelier's principle. As you consume ammonium ions, it pushes the top equilibrium to the right. And again, ammonium ions, top left in this, it's a conjugate acid or weak base, and so it is acidic. Will magnesium hydroxide be more soluble in a solution with high pH or low pH? And so again, magnesium hydroxide dissolves in magnesium ions and hydroxide ions. Then again, we have that polyatomic ion, the hydroxide ion. Remember, polyatomic ions stay together as a group. And so hydroxide ions should react with hydrogen ions to form water. You should recognize the Ekman constant for that reaction as being 1 over kW. It's very, very large. And so the lower the pH, more hydrogen ions you'll have. And so magnesium hydroxide should be more soluble the lower the pH. This is actually related to milk of magnesia, which is used to sometimes soothe people's stomachs. It consumes the stomach acid. Now, milk of magnesia is actually a suspension of magnesium hydroxide. Now, in water, it doesn't really dissolve. It has a very small KSP, but your stomach has hydrogen ions. Is very acidic, and so when the milk of magnesia gets to the stomach, the acid consumes the hydroxide, and it takes this reaction to the right.
Milk of magnesia, a common household product, consists of a suspension of magnesium hydroxide in water. Magnesium hydroxide is relatively insoluble in neutral water. However, it dissolves in an acidic solution. At the molecular level, solid magnesium hydroxide consists of layers of magnesium cations surrounded by hydroxide ions. When solid magnesium hydroxide is placed in water, it does not dissolve. In an acidic solution, there is a high concentration of solvated protons, the hydronium ions, H3O+. The hydronium ions attack the hydroxide ions on the surface of the solid, forming 2 molecules of water. In the process, magnesium cations are released to the solvent. Assuming that hydrochloric acid is used in this reaction, the overall chemical equation is as shown here.
And so again,
the net ionic equation for the reaction is this.
And so again, milk of magnesia.
The equation emphasizes that any strong acid in water could react with solid magnesium hydroxide to dissolve the solid.
And so again, milk of magnesia is a suspension of magnesium hydroxide, means it's got little solid particles of magnesium hydroxide, which dissolve when it hits an acid because the acid reacts with the hydroxide ion. We could also look at a slightly different reaction. So here we have cobalt ions and hydroxide ions, and when we combine the two, we get cobalt hydroxide solid.
When we add an aqueous solution of sodium hydroxide to a solution of cobalt-2 nitrate, precipitation of cobalt hydroxide occurs.
Now the reaction as shown is just a net ionic equation. The speculator ions are not being shown. And so notice that we got concentrations, they're stable, and so that means the system should be at equilibrium. Now a question we could ask ourselves is there any way that we could redissolve the cobalt hydroxide? Well, if we look at the reaction, if we can consume the hydroxide ion, then the cobalt hydroxide will dissolve. Well, hydrogen ions will react with hydroxide, consume the hydroxide, and so that pushes that top reaction to the left. And so all we should have to do is add some acid.
If we then add an acid to the mixture, the cobalt hydroxide dissolves. Most insoluble hydroxide salts can be dissolved by the addition of acid to the solution.
And so notice we're back at equilibrium. The concentrations are again relatively stable, Now if we take the cobalt and hydroxide concentrations before we added the acid and we put those into our chemical expression, we would get our value for KSP. If we take the concentrations after the acid has been added and the concentrations are stable, we'd actually, and put those in our expression for KSP, we'd get exactly the same KSP value. And so please remember, most chemical systems are more complex than the examples that typically we talk about. Typically there's multiple equilibrium, and we have multiple equilibrium, all the equilibria have to be satisfied. I hope that helps.